Okay, so let's start. As I mentioned, we'll start with an overview, really brief overview of fertigation and irrigation um, practices. So we'll start with fertigation. So fertigation basically is the application of fertilizers through the irrigation water, right? That's what it means. It's like the combination of the two words, fertilization and irrigation. And because of that, there's many systems, many irrigation systems to which you can inject fertilizers, or you can inject fertilizers to the irrigation line. That would be fertigation. So pivots, through pivots, we can inject the fertilizers to the irrigation water. So fertigation can be also with pivots. What I want to say here, fertigation is not only drip systems, okay? Sprinklers and drip systems, of course, and also hydroponics is also a kind of fertigation, okay? Because and in fertigation, we usually talk about nutrient solutions, not always. I will explain that, okay? So some say the chat is disabled, so just put your questions in the Q&A section, and that will be fine. I'll see everything. So, what are the agronomic benefits of fertigation? So fertigation enables us to apply nutrients where they are needed. That means in a more specific manner to the plant. Also, when the timing of the application of fertilizers can be better controlled when we use fertigation. And the reason is simple. If we just go into the field and spread fertilizers, I don't know, with a tractor or in any other mechanical way, then of course we might not be able to go into the field because the crop is too big. There are many reasons, and of course it also requires a manpower. So once you have a fertigation system in place, it's much easier to control the timing of the application of nutrients and water, of course. And the timing is for nutrients is, of course, very important because this gives us the flexibility or the ability to apply the nutrients when the crop actually needs them, because the absorption rate, the uptake rate of different nutrients varies throughout the growth of the crop. So the rate is not the same. If we apply most of the fertilizer at the beginning of the season, when we don't have fertigation, then we cannot really control that. But with a fertigation system, we can say, all right, now we increase the rate, now we decrease the rate, now we apply more phosphorus, now we apply more nitrogen, etc., or less. So it really gives us a lot of flexibility here, and therefore it improves the yield and quality of the crop. And of course, sorry about the typo here, but in drip irrigation allows us, for instance, to directly apply the nutrients and water to the root system of the crop. So in some fertigation systems, we cannot do that, like in pivots or with the sprinklers, right? But when we talk about drip irrigation, then really it applies the nutrients and the water directly to the root system of the crop, and that's, of course, a more efficient. Another agronomic benefit is that it minimizes leaching. So this is both agronomic benefit and environmental benefit of fertigation, because some nutrients, especially nitrogen in the nitrate form, they tend to leach. Okay, to leach, it means they go below the root system of the crop, and it becomes an environmental problem when it gets to groundwater, right? But of course, that if, for instance, nitrogen leached below the root system of the crop, then the crop cannot absorb or cannot use the nitrogen. And in fact, according to studies, approximately 60% of the nitrogen we apply is not being used by the crop. due to leaching and other reasons. There is leaching, there is a volatilization, etc. But using fertigation increases the efficiency of nutrient uptake. Okay, that's why we say there is higher efficiency when we use fertigation, and particularly drip irrigation. Of course, when we talk about nutrient solutions in soilless media, it means growing in containers, in substrates, or in hydroponics, then we really talk about very accurate concentrations levels of nutrients in the nutrient solution. We're talking about, and then we talk about parts per million, which means 1 part per million is 1 gram per cubic meter of water. All right, it's a very small amount. All right, so in nutrient solution, we already talk about parts per million concentrations in parts per million of nutrients. And we can get very, very precise here. I'm not sure I have this example in this presentation, but maybe I'll bring it up. It's interesting to see how precise we can get. Another advantage here is reducing diseases, and the reason it can reduce diseases, depending again on the irrigation system. I mean, pivot will still, or sprinkler, any sprinkler system will still wet the leaves, but in drip irrigation, we avoid that. So we don't wet the leaves, and that reduces diseases, plant diseases. Now, also, there are some additional scenarios in which fertigation can offer benefits or sometimes must be used, all right? So in sandy soils, for instance, think about sandy soils, and sandy soils do not retain nutrients, or they can hold a very small amount of nutrients. And therefore, the fertilizer application, the nutrient application must be more frequent, right? Unlike, let's say, clay soils, all right? That can retain the nutrients, they hold the nutrients, and then these nutrients are served as a reservoir, okay? Or the soil becomes a reservoir of nutrients, but sandy soils, they cannot hold or retain the nutrients, and therefore fertigation can offer a very important benefit there, because then we can apply more frequent fertilizers or nutrients more frequently, as I mentioned before, when we need them. And also, of course, in container grown plants and hydroponics, where by definition it's a fertigation. And also another benefit or advantage is that fertigation allows us to adjust nutrients or fertilizer rates and water during unexpected events, or as a result of unexpected events. For instance, if it was raining, right, and nitrogen leached, right? If we have fertigation, we can compensate for that. Or another scenario, or let's take a scenario where we don't. Actually, yes, when we have a fertigation, we can even decide if we had, let's say disease, right? There was an occurrence of a disease that we know that it will reduce our yields. So then why apply all the nutrients or the fertilizers that we planned to apply? Maybe we can reduce them and at least save money and protect better the environment. And so there are different scenarios in which the flexibility in applying fertilizers or increasing the rates, decreasing the rates can be a benefit. So fertigation doesn't come without challenges. There are many challenges with fertigation. I would say that the biggest challenge is that it's not easy, right? Why is it not easy? And I'm not talking even about doing the calculations, understanding how much we inject and how we inject the fertilizers. But there are issues. There are issues with the clogging of emitters of parts of the irrigation system due to precipitation of minerals, fertilizers or minerals, if we don't dissolve them well, or if we mix the wrong together. fertilizers that are not compatible, then we might get precipitation, we might get deposits. If they react, the fertilizers, with elements in the water. So this is all very sensitive. Think about it. We dissolve a fertilizer, a salt. A fertilizer is a salt in the water, and then we inject this through or we apply it through emitters, which are basically have a tiny openings, all right, and these might be clogged. So and then we have another two issues, which is a calibration. The systems must be calibrated, and trust me, I've seen hundreds of fertigation systems, and I can tell you that, in fact, I would say even most cases, right, the systems that I saw were not calibrated, okay, or required a calibration, because having a technology but not having it well calibrated actually takes out all the advantage of it. I mean, it's not as efficient as we would expect it to be, and we might even do cause damage, right? And have mistakes. And so there is a very large room for mistakes with the fertigation, unfortunately, but that's the situation. And so we need to well calibrate the systems and really make sure that they are working properly. Okay, and just few examples. Okay, there are automated systems. We'll see examples with sensors, EC, pH sensors, and everything, which looks great, right? But if the sensors are not well calibrated, then we might not apply the right rates of nutrients that we want. Or if the injectors are not calibrated, the system thinks that we apply a certain rate of fertilizer or stock solution, right? But in fact, it gives another rate. So many things there. It relates to the flow rates of the irrigation, the flow rate of the irrigation, the flow rate of the injector, the injection ratio, the capacity of the system. So there are many factors that the concentration of the nutrient solution, many factors that affect it. So calibration is extremely important, and I see a lot of confusion around this, even in the more simple systems. All right, and another challenge is, of course, the maintenance and support we get to these systems. But I talked enough about challenges now, so let's just continue. I see your questions. I see your questions about injection ratio. I will mention injection ratio here, and we'll see that a very important concept in proportional fertigation. Let me just pause for a second because their questions are accumulating. Okay, I'll skip. I see here specific questions about nutrition, and I'm sorry, I'll try to answer at the end about these questions. Now, there are basically two fertigation approaches or methods, we can call them, and one is the quantitative fertigation, and the other is proportional. And what's the difference? They are both fertigation, right? So here we see some examples of fertigation systems. Right, so some of you at least think about it, which one is proportional, which one is a quantitative. So I will not make a poll here, right? But I'll just say it. So these two, the ones at the bottom, are both quantitative fertigation systems, which means in quantitative fertigation, we simply dissolve the fertilizers in water and apply the fertilizers through the water. For example, if we need to apply 10 pounds per acre of potassium nitrate, all right, then we dissolve 10 pounds, or if it's a 1 acre plot, if it's more, then we do the calculation. We dissolve the amount in a certain amount of water, like here. Let's say we have a tank, we dissolve this fertilizer in the tank, and we apply the amount that we need. All right, and here in a quantitative fertigation, the concentration in the water, the concentration of the fertilizers in the water is not a constant, okay? Because we just dissolve the fertilizer and deliver it to the field together with water. It can be at the beginning of the irrigation, some do at the end of the irrigation. It depends. In fertilizer tanks, by the way, this is a fertilizer it's the most, I think even the first fertigation system. You have a tank where you put the powder, the solid fertilizer, and then water just goes through the tank and dissolves the fertilizer as it goes to the field. I think I have let me just see here. Yeah. So in proportional fertigation, it's more sophisticated. And why? Because here we usually we talk about concentrations of fertilizers and nutrients in the water, not necessarily amounts, not in amounts per area, not pounds per acre or kilograms per hectare. We're talking about parts per million, as I mentioned at the beginning. We're talking about milligrams per liter. 1 part per million equals 1 milligram per liter. It's the same. So here we have injectors that take a concentrated solution, fertilizer solution from a tank, and injects it proportionally, right, into the irrigation water. And here comes the concept of injection ratio. There was a question about it. Okay, for example, injection ratio, the easiest way to understand it is to talk in terms of percentages, right, of percentage. So, for instance, 1%, all right, here it's a mechanical system where it doesn't require electricity for the injection, for the irrigation, of course, it needs a pump. But here you basically adjust, this one is called dosentron, but it's a specific brand. But you adjust it, for instance, to 1%. 1% means that for each 100 liters of water that goes through the system, the irrigation line, right, it will inject 1 liter of fertilizer solution. So each gallon of water gets the same amount of fertilizer as the other, okay, as the previous and as the next. So each liter of water get the same exact amount of stock solution, right? And that's the injection ratio, is how much, all right, of the stock solution. Not of it. We don't even talk sometimes about, when we talk about injection ratio, we don't talk about what we have in the tank. We're just about what's the injection ratio of the system, all right? So we can adjust it. And in the automated systems, we have more control because we have the computer, we set up the injection ratio for each injector here. And I don't know if you noticed what I've just said, you can even set an specific injection ratio for each nutrient, each fertilizer. And this gives you a lot of flexibility, of course, because you can change the ratios between nutrients. For instance, different uses. You have, I saw fields where you have, or farms, we have a greenhouse and open field, all right? One next to the other, using the same fertigation system. So you apply certain nutrients or fertilizers to one, others from a different tank to others, or different ratios between the different stock solutions between the tanks. So again, it gives a lot of flexibility, allows for a lot of optimization, and the control systems, as I mentioned before, they have many times EC and pH control, where that's another layer of I would say adjustment, optimization, where you can actually say, all right, I'm applying, I want you to the system, you configure in the system, and I want you to apply a certain rate of or certain injection ratio, all right, but also make sure that the EC, the electrical conductivity, all right, of the water. By the way, for those who don't know, electrical conductivity, EC, is a measure to the concentration of fertilizers in the water, in the nutrient solution. So basically, higher EC means higher fertilizer concentration in the water. It doesn't tell us which nutrients we have. It doesn't tell us the ratios of nutrients, but it tells us the total, say, salinity or total concentration of fertilizers in the water. So in those systems, you can set limits and targets. You can say, I want EC of 1.5 decisiemens per meter, all right? And then the system will automatically adjust the injection to reach this EC level. It still doesn't tell you. Again, I emphasize that because that's extremely important, and we'll see that later in the platform. It still doesn't tell you what exactly you apply. You need to do to calculate this. So that's about fertigation, really, in a nutshell. Just from time constraints, I could talk for hours about fertigation. Let's just now go briefly. This will be shorter over water demand of plants. So of course we have all what's related to the soil and how much water it can retain, how much water it can release. I'm not going to talk about this today, but I do want to talk a little bit about the water demand, water requirements of plants and how they are determined. Okay, so basically the water demand is actually determined, I would say, by what we call evapotranspiration. Okay, and evapotranspiration is the amount of water that is lost to the atmosphere through plants' leaves and the soil surface, right? Because we have the soil surface, water evaporates. That's what it's about, why it's called evapotranspiration. It evaporates from the soil, and through transpiration, plants, it also being lost to the atmosphere through the leaves of the crop of the plants. So that's evapotranspiration, and there is a term which is the reference evapotranspiration. Okay, ET0, where it's the evapotranspiration rate of a reference surface with specific characteristics. Okay, so this is a standard. All right, basically it's, never mind, it's a grass at a certain height, etc. But it's like saying, hey, if how much water would be lost from this kind of surface, right, with plants and soil and so on. So that's the reference evapotranspiration. But how much water will the plant really, the crop really absorb? And that, here I have the definitions for that, but never mind. But that depends on the crop, and I will explain about that in a second. So how do we assess? How do we estimate the reference evapotranspiration? One method, very basic, okay, is the evaporation pan. So as you can see, there are farms with evaporation pans, where this pan is a standard pan that allows you to measure how much, what is the rate of evapotranspiration, of the reference evapotranspiration. And another very common method is, of course, using equations and models, and this is used by services also that provide the reference evapotranspiration, and it uses different parameters, net radiation, wind speed, saturation pressure deficit, etc. All right, so there is the model or mathematical way, and there is the evaporation pan. Today there are some other methods that I will not mention here. And now it brings me to the crop evapotranspiration, to the ETC. It's called ETC, the evapotranspiration of the crop. By the way, if we did not mention, we we measure evapotranspiration in units of depth, right? Millimeters or inches, okay? So, and basically the evapotranspiration of the crop depends on the development stage of the crop, okay? And that's at each development stage, the crop we can set or we can assign a KC. A KC is the crop coefficient, okay, which depends on the crop stage, and it's actually the fraction of the evapotranspiration that the crop would actually use or lose, I would say, yeah, and the amount of water it will consume. So, for example, and then the evapotranspiration of the crop is that KC, the crop parameter, times the reference evapotranspiration. Okay, so if, for instance, we have reference evapotranspiration of 10 millimeters per day, and the KC at a certain stage of the crop is 0.4, then the water requirement of this crop would be 0.4 times 10, and that gives us a 4 millimeters, right? And of course, there are more sophisticated methods for that. There are different there are other types of a KC, but basically this is the way to determine the crop water requirements. Now, the challenge here is, of course, to know what the KC is. All right. So there are tables for that, but there are also technologies to allow us to know the KC, and of course the evapotranspiration. So let's say continue with a demo of yieldsApp, specifically on fertigation and irrigation, because there are many features to the platform. So let me just pause for a second again for just a few questions. A question about recording. As I mentioned, I will share the recordings, and there is a question about determining phosphorus in the soil. So it's not very related to our topic today. Okay, you can write me an email, and let's say continue here. All right. So I'll stop sharing and I'll share again my screen, and bear with me for a second. All right. Okay. So let's see today how we can plan fertigation and irrigation using yieldsApp, which is a platform that covers most agronomic practices, which means pest and disease management, and plant nutrition in soil and in soilless culture, and irrigation in open fields. All right. So let me start with fertigation. Okay, let me start with fertigation. I'm really going to go to deep dive into those features. So I'll show you here. Let's take this this one, at open field. It's this one. I'm sorry for that. All right. Yeah, let's see this one, for example. Okay, let's see this one. So here on the dashboard of, let's start with a vegetable or leaf vegetable, in this case, lettuce. There are many crops in the system, so I just chose 3 for this demonstration. We have a corn, a tomato, lettuce. We could do also some orchards like lemons, citrus, avocados, whatever. But okay, let's see those examples. So here on the dashboard, and let me just go to the fertigation part. Okay, let me just go to the fertigation part. So basically, I go here to fertilizer plans or to field tests if I have If I have a field test like irrigation water analysis, soil analysis, tissue analysis, this can be all applied and imported into the platform. Let's even see that. I think I have something that's just for this demo here. Okay, it's the same. So we can upload our soil test, our tissue test, the water test, and then design a fertigation programs. Okay, let's start with a simple one for open field crop, as I started before. And this lettuce, I have my water analysis. And let's see it. I wrote corn here for the, but it doesn't matter. So we have a water analysis. It gives us the interpretation of the nutrients in the water. But now we want to do the fertigation plan. So what do we do? So over here, I'm adding a new. I went to fertilizer plans, adding a new plan, and give it a name. Example fertigation. Right? A zone in this field, I have only one zone. It will automatically bring up the nutrient requirements, right? The reference nutrient requirements. I see there are some raised hands here. Please write in the chat, okay? It will be easier in the Q&A. I will see your questions and I will answer it, all right? I have here, also have my target yield here. This is remember, this is in an open field in soil. I defined this field to be open field in soil. And I now want to create the fertigation plan. So what I want to do here, I want to go to field tests first, okay, and basically select the field test for this crop, all right. So let's take it from all fields. Let's assume that I took a sample in a near field, okay. So I'm going to use a certain field test, and I'm going to save it. I can also use the soil test, and then all I need to do at the first step is to generate recommendation. Now, fertilizers, I will explain about this. I will go deep into that, right? We can define default fertilizers, right? Or we can actually select fertilizers as we do the fertilizer plan. But let me first show you how this works here. So once I generated the recommendation, it instantly gives me the rates of fertilizers to apply. Okay, and this is per zone or per hectare. Let's see, per hectare will be easier. Guys from North America, I'm sorry. Well, I can show it also in pounds per acre, but just think of the kilograms per hectare as pounds per acre in this case. All right. So it gives me here the required fertilizer rates. Okay, over here it told me that with the fertilizers that I had available, I didn't reach the potassium and the calcium. We can check that. I can look at it and see what was the issue. So over here we probably need another source of potassium. Okay, so we might need another source of potassium here. I can select a potassium sulfate, I guess. Let's see if it's selected. So here, let's see here that we can select what we had. All right. So we have it. And then what I want to do, I can go to and select the application method, which would be in this case, we can select either quantitative. Remember, we talked about quantitative and proportional, or proportional. All right. So let's assume that I now go first to a daily schedule, right? I want daily schedule, and I want a proportional fertigation, right? So I do that. First, it gives me the rates of fertilizers per hectare per day in this case, and then I click on fertigation. All I need to do here is to click on generate a fertigation, and look what happened just here. So what happens here is that it automatically yields up automatically It distributes the fertilizers to tanks. Okay, here in this case, I have 2 tanks, all right? But it might be more if I adjusted also the acid, for example, or if there were more fertilizers that are not compatible. So it might recommend, we'll see another example, 3 or even 4 tanks, all right? And it also tells me exactly how much to dissolve in each tank, all right? So here, for instance, calcium nitrate to dissolve 471 kilograms. For most of you, this will sound a lot. Now, what's the reason for that? The reason is that the solubility of calcium nitrate is high, all right? So basically, what I want to do here is it gives us default injection ratio and tank volume, but we can and should adjust this because these are system parameters. So injection ratio, let's make it in percentages for you to be easier for you. Let's assume 1%. If I inject 1%, right, from a 1,000 liter tank, as you can, I don't know if you noticed, it changed the amounts of fertilizers that I need to dissolve in this tank. All right. So it tells me, all right, here now with this injection ratio of 1% and 1,000 liter tank, dissolve 23 kilograms of calcium nitrate, 780 grams of iron, EDTA, HA, etc. Right? So I can change both. I can adjust both the tank volume and the injection ratio. Let's make a tank volume of 200 liters. Right? So here are the rates to dissolve in 200 liters. Tank with 1% injection ratio. Right? I can do the same here. I can put here. And again, depending on my system. Now, note that it will give me by default, it gives you the minimum required injection ratio. What's the minimum required? Let's go below the minimum. Let's go to 1, right? Oops, I get a message, an alert. Why? Because what it tells me here that in order not to exceed the solubility limit of a fertilizer, I need to have the stock solution, the solution at a certain concentration, which means if I inject less, all right, let's assume that now I injected, I configure the lower injection ratio. That means that I will need, in order to get the same concentration, remember this is proportional for irrigation. So in order to get the same concentration of the nutrient or fertilizer in the irrigation water, I will need to dissolve more fertilizer in the tank because I'm making so I have to make the solution or the stock solution more concentrated. If I inject more, if I inject a lot, right? Now let's say inject 10 liters per cubic meter, then of course I need to dissolve more fertilizer in the tank in order to get the same concentration in the irrigation water. So now when I went below the minimum required, in this case, it exceeds, all right, the solubility limit of the fertilizer, which means that injecting 1 liter per cubic meter, all right, is risky, all right, is risky because I will have to dissolve or to have higher concentration of fertilizers in tanks, and that might cause precipitation. The fertilizer will precipitate. Now, this could be a result of the solubility limit of a specific fertilizer. This could be a result of interaction between the fertilizer and the water. So it also depends on the water quality and in which we mix the fertilizers, or just interactions between fertilizers, which means that at a certain concentration, it's okay to mix them together. But if we increase their concentrations, then we already might already get a precipitation. So by default, it will give me the minimum required. So here, remember we said 1%, we want 1%, and here we go. Okay, so that's here. Remember, I selected the daily one, so it tells me from day 1 to day 19. This is what I need to do. And note here, we also have the EC, the electrical conductivity. So it also estimates or tells you what the EC of the water with the fertilizers should be. All right. And that's also very important because this allows you, one, to test it in the field to make sure that this is what you get with your system, and two, in the automated systems to adjust the EC on the system. And then, of course, I can save it and I can go to the next one. All right. So here I saved it and I'm back. But by the way, I could just apply fertigation to one of the stages, for instance, or I can do it for the additional ones and go stage by stage. All right. So that would be a proportional fertigation for an open field. Okay. Let's see another example here. Let's go to the corn, and what I want to show you here before that, and we'll get back to this section of the platform. Here we have the crop monitoring, which means that it tells us at which stage the crop is, how many days are left for harvest. And here you can see many days for harvest, although it's in R2, but that's because I just planted it, all right, in colder conditions, all right, in the colder weather. So it takes the weather, and based on that, with using artificial intelligence and modeling, we know very precisely when the crop will mature and when it will go from one stage to the other. Also very important for the irrigation, as you'll see in a minute. But let's see here. So over here, it's also important for fertigation in soil, for instance, is to introduce the soil test results. All right. And we use all this information. I'll show you what information we're using. But some of the information here is, of course, the information that you upload, and you can upload it in the click of a button, basically. So a soil test has it has a location. It can be within the field, all right? We can use the different tools here, different indices, also to plan where to take soil tests from. Again, it's not the topic of today, but when we do a fertigation plan, if we want it to be for open field, if we want to optimize it, then it's highly recommended to have the water quality and to have the soil test, at least. So a soil test has a location, and we can introduce the soil test data, and it, of course, will interpret this data. So let's see here. Again, it's the numbers here, and it will give me the interpretation of the soil test results. Right, so it tells you whether it's adequate, high, low, etc. It really depends also on the lab, which means on the extraction method that the lab uses. Right, so there are all the extraction methods over here, and we can even configure a specific lab per account. So users don't have to select now extraction methods if the lab is configured. So it will interpret the results. Here we have for all nutrients. And so we have the soil test, we have the water, and in fertilizer plants, once again, let's see one that I already prepared. All right, so we have the rates. Now, if I go to field tests, you can see that I already selected here. This is in Spanish, but it's a leaf analysis, foliar analysis, and soil analysis. Right? And based on that, on the crop model, on the weather, the crop development, satellite imagery that we obtain every 5 days from different sources. I'll show you some interesting stuff about that. All right. We generated the fertilizer plan. Again, here it's per hectare. And let's see an example of quantitative fertigation, right? Not proportional. And what it will do here, let's assume that I want to apply these amounts now, which are high amounts in this case. I want to apply them through irrigation water, let's say some way. Okay, then I can select here quantitative fertigation, and here we don't have injection ratios. I go to fertigation, and when I generate it, when I generate the fertigation, it will already give you now the field is large. That this is a very large field, all right? So you need a very large tank and high fertilizer amounts, but it will tell you exactly how much to dissolve, what the tank volume should be, and how much fertilizer to dissolve in the tank. So here in quantitative fertigation, it's more about what size of tank you need, all right? What size of tank you need in order to avoid precipitation, deposits, and clogging of the irrigation system, etc. All right. So we have that. We've seen two methods. One is the proportional in open field. The other one is proportional, is a quantitative, right? But what about the hydroponics and things like that? So let's see. Actually, before that, let's see here an example. I prepared, I think, for a greenhouse. Okay, but this is greenhouse in soil. Greenhouse in soil and greenhouses in soil, what we usually do, we don't work in a quantitative fertigation usually, right? There are growers that do that as well, but we use the proportional fertigation. So over here, what we're going to see is a nutrient solution. What do I mean? The targets here in this case, and that will be the same, by the way, to sandy soils and to hydroponics and to containers, right? If I go to the nutrient planner, it tells me the concentration, the requirements, not in pounds per acre or kilograms per hectare, but in parts per million, okay? In parts per million in the nutrient solution. So here, the figures that we see here, for instance, let's take the flowering stage. Okay, we're going to need 230 parts per million of nitrogen. Out of which 190 are nitrate and the 40 are ammonium nitrogen, right? And phosphorus 44, potassium 318. So it uses very smart way to determine the nutrient requirements, including the water and the soil, the leaf analysis and all that. So we have those required nutrient concentrations, which are, by the way, also very flexible. I mean, you can make adjustments, right? So agronomists sometimes do adjustments. They want to say, all right, no, I want here 250 parts per million, right? All right. So they can change, they can modify that, and they actually do have a lot of flexibility in adjusting those recommendations, right? Even by adding rows and removing rows, etc. So that's one thing that I wanted to show you. The other thing would be, again, in fertigation, also here, note that the fertilizer rates that we see here when we talk about nutrient solutions is in grams per cubic meter, okay? Which is equal to ppm, but this is the grams per cubic meter of the fertilizers, not the nutrients yet. Okay, what we saw here in the nutrient planner was the nutrients. And so now I can do the same as I did before. Click on fertigation. If I select acid, it will also calculate the pH, of course. And then for each stage, I get the fertigation program. Okay, here I already adjusted it to injection ratio of 5 and volume of 1,000, right, in all tanks. I didn't select an acid, so I can do that as well. Let's see it. I can go ahead and say, all right, I'm choosing here, let's say sulfuric acid, okay? Sulfuric acid, 98%, and I want to also, I want to adjust the pH. Need to adjust the pH as well as a target if it was not defined, in case it was not defined. Don't remember if you already defined it or not, but we'll see in a second. Here, no, I didn't with the acid because I didn't define it here. Okay, or it was the pH of the water was already 6.7. That's the thing here. So if the pH of the water is higher, then it will add acid. In this case, acid was not required. All right. And by the way, after generating the recipe or the program, you can check it, all right? You can make sure that everything is on close to what we wanted or at what we wanted. What we see here is interesting. All right, we defined certain ratios of ammonium and nitrate, right? However, right, with the fertilizers that we had available, we couldn't exactly reach. We did reach the nitrogen, the total nitrogen, 100%. However, the ratio is not what we actually wanted. And of course, for that, we'll need to select other fertilizers, okay? And so as I mentioned before, we have flexibility with the fertilizers. You can predefine your default fertilizers, or for each plant, you can select a specific fertilizers, which does not necessarily mean that yieldsApp will use all the fertilizers that you selected. It just means that those are the fertilizers that it is allowed to use for the recipe for the fertilizer program. Okay. Now let's talk about fertilizer for a second, because I already mentioned that you have here the option to define your default fertilizers. Okay, which means default means the ones that it will use every time, all right, or it will have available every time without the user, without you having to select fertilizers specifically. Okay, so that's what it does here, and you can also add products, add the fertilizers in a very easy way. So we can add a fertilizer, include its composition, and save it, and it will be available in the platform. And also you can define prices, your price list, and it will optimize based on the pricing. So this is regarding fertigation. Again, I can go on, but I think we went through the basics here of how you do that. You saw how easy it is, a few really seconds to design fertigation programs that are accurate and, of course, suited to your specific, to your crop and to your crop conditions. That's also super important here. Okay, to your field conditions. What I want to show you now is, let's talk a little bit about irrigation planning. And you guys see some questions here. Let me see what I can answer now. Okay, question from Nestor. To implement precision fertigation, what sensors, hardware need to be set up in the field? All right. Okay, so let me go back to that. I think it's an important question. I can show you. By the way, we even have a presentation about precision. Fertigation is precision ag tool, right? But basically, you're talking about this kind of systems, okay? Talking about this kind of systems where's my cursor? One second, my cursor disappeared. So let me just. It's almost back, almost. Oh, it's back. I think. Switch presentation because here it's more second. And let me stop sharing, share again with the presentation, because otherwise the cursor disappears. And so I'll show you here. You can answer your question. So basically, we're talking about this kind of systems. All right, we're talking about systems that include. Go back to this. All right. You have what we call the table, all right, where you have the injectors. Now, how many injectors do you need? For instance, how many tanks? An injector is almost equal to tanks. How many tanks, how many injectors do you need? That will depend on your crop, on your conditions, even on the water quality. Think about water with high calcium and magnesium. So if your water source contains high concentrations of calcium and magnesium, then you might not need to use calcium and magnesium in your nutrient solution, and that saves you a tank. So this can also help you here design your system or tell them what to do, because otherwise you might spend money that is not necessary. So one is to select to know how many injectors we need, how many tanks, how many injectors we need, how many valves we want to use. That's also important. Remember, we talked about the injection ratio. I saw many cases, and trust me, when people design their systems, if you do this mistake, then it becomes hard, right? It becomes difficult to manage, because the injection ratio, right, is determined also or affected by the flow rate. Okay, sometimes I go to farms, I see they operate 4 or 5 valves at a time, all right, and with a certain injection ratio. However, the system doesn't have the capability, because of the flow rate of the injection ratio, to apply this rate of the required rate of fertilizers for this high flow rate of water. I'm not sure if it's clear, because it needs more explanation, okay? But it's all related. It's the crop nutrient requirements, it's your water quality, it's your soil quality and composition, okay? And then for precision fertigation, of course, you need the EC and pH on the system. Highly recommended to have flow meters. Okay, you see here, you have a flow meters where you can adjust the flow rate of each injector. Right now, here it's very important, because this is a machine, this is a robot. But these flow rates, these flow meters are usually mechanical, which means, right, that you have to configure or to set up, right, in the configuration of the system, you have to set up the right flow rate. That means if you adjusted here a flow rate of 200 liters per hour on the computer, on the control, you must also have 200 whatever number I said, I don't remember the same number, okay, the same flow rate. Otherwise, the system will not work correctly. Okay, so you need injectors, you need the controller, you need the EC and pH meter. Usually they come together, right? Those companies, they offer the full package, all right? And you need good planning. You need good planning for that. So let's go back. Okay, a question for intercrops. About intercrops, calculate the nutrient rates. Again, over here, you can do it because you have zones, okay? Over here, if I define, let's go and define a new field. Okay, I can define a new field. Let's call it an example, all right? And I can go ahead and let's just draw this field over here. I will not do it accurately. This is just for an example, but I make it with zones, okay? And then I can actually draw different zones within this field, okay, for the intercropping. Okay, and then this allows me to manage everything, basically. Nutrients, irrigation, pest and disease management, if we have all the right equipment to apply such recommended. But basically you can one option for you is to plan for each zone specifically, and the other option is to use it as one field, and the platform knows how to handle this. All right, we have very strong agronomy here in the platform. But let me just continue to irrigation because our time is over. So I just want to go over the irrigation here. So and let me see here. Go to this field. Things that we had rain. But yeah, the system knows it. So let's see here. I want to show you a few things about irrigation. First, let's go see the irrigation planner, the water balance. Okay, so here the platform gives us a very accurate water balance, which takes into consideration the growth stage of the crop, and then the crop parameter. It gets the correct crop parameter at every single moment, right? And of course the precipitation, and it gives you the balance. All right, so what we see on the graphs, the blue one is the precipitation from the selected date. It means from, in this case, from February 15th. So we see we had some rain here, and the accumulated evapotranspiration, crop evapotranspiration, again from the selected date up to today. So we can see that for now in this week, all right, or this time range. And again, and also a forecast for the next 2 weeks. All right. And so over here, what do we see here? We see the precipitation until today from February 15th, which was 57 millimeters. The crop requirement, the evapotranspiration of the crop, was 17 millimeters less, which means that if you look at the bottom line where it says water balance from the selected date is 0. So basically now I don't have to apply water. We'll go to 1 week before or 2 weeks before. And it also populates all the other important information, the daily evapotranspiration, the reference evapotranspiration, which is 2.61, and the KC of the crop. By the way, you can see that now for this crop, for the corn, the KC at this stage is higher than the reference evapotranspiration. I mean, higher than 1. Yeah. And then the daily irrigation requirements. So how do I plan my irrigations? Let's go 1 week before, when there was, or 2 weeks before. Let's see. Let's make it from February 1st. We said to let's say February 8th, for instance. February, it was still right there. Okay, this is a good example here. All right, so I hover over this point before the rain. I just but let's take the right date here. Let's take January 18. Okay, great. So I'm taking January 18. So let's assume I'm here on January 27th. All right. Last time I irrigated was January 18, for instance. Okay, so I'm taking my last irrigation date, and it tells me, if you look at the bottom line, it tells where it says 19.19, 19.1957, right? So from the last date of irrigation until today, this is the amount of water that I need to apply now. Of course, it also gives you the daily evapotranspiration, the KC, the daily evapotranspiration of the crop as well, not just the reference. And basically it tells you exactly how much water you need to apply. Now, you might ask, based on what, right? So the crop evapotranspiration, right, or the crop parameter. The crop parameter is very important. We need to obtain the right one, because this will eventually determine how much water we need to apply, in addition to the reference evapotranspiration. And this is done by both by AI, right, combining it with the scientific data and with satellite imagery, right, because we check the status of the crop every few days, right? I'll show you that in a second. Based on all that, we have algorithms that determine precisely the crop coefficient, and allows us to do very accurate water balance, right? As you can see, it gives you the daily and from any selected date. Now, I'd like to show you something with the satellites. With the satellites, we do continuous monitoring of the crop. And over here, you probably know NDVI, which is the most standard vegetation index, all right? But there are other indices that can be even more important, okay? Because NDVI, by the way, as you can see, of course, at this stage of corn, is already saturated, okay? So the green, it gets to a saturation, right? And then you don't see variability in the field, you don't see much, right? Let's see some other stuff here. Let's see here, the NDMI. NDMI is actually the water status of the crop. How much water in the leaves? I mean, in the crop itself, not in the soil, right? Here we see quite a good correlation, probably because of the rain, between the NDVI and the NDMI in terms that they're both green, but I want to show you something where it's not the case, how it identifies how it identifies water deficiency, for instance. So let's take here a barley field. This is let's see here. I want to show you this water deficiency. In a sec. I will, until it closes, I will answer another question here. The minimum size, which will be economically feasible to invest in precision fertigation, depends on the crop. It really depends on the crop. Fertigation is basically something that is recommended. Okay. Usually, by the way, in greenhouses, even from less than a hectare of a greenhouse, you already have fertigation systems. But an automated fertigation system, just that you know, the cost is about, I don't know exactly, but I'm just from my memory, around $20,000 or some $15,000, $20,000. All right, let's see here. I want to show you something. So over here, we have this field where we can see the NDVI, or there's different plots here. We obviously see that there's nothing here, but over here it's quite green, right? But let's go to the NDMI. And you can see that the NDMI is not great here, for sure not here, although we had your lower NDVI. What does it mean? It means two things. It means that although the biomass is high and is fine, in this case, for now, right? The crop is getting dry. There is an initial, or there is some kind of water stress already, okay? Because you remember before, we saw the crop is with the NDVI is high, the NDMI, the water index here, it was high as well, which means that the status of the crop is fine over here. It's a different situation. We see that the water status is low. By the way, in certain cases, it's what we want. Sometimes we want to have water deficit in some crops, or even before harvest. All right, sometimes before harvest we dry the crop. And many crops will do that. All right, and we want to harvest at a certain moisture status. Then, of course, this allows you to manage all that. Okay, to make all the adjustments. Plan the harvest time based on the moisture of the crop. In this case, it shows a water stress. All right, so that's what I wanted to show you over here. And another thing that is super interesting, and we found out that it is related to two parameters. One is the moisture of the soil, all right, and let's go here. And the moisture of the soil and the height of the crop, right? And now, so this index is called RVI. Even more interesting here, because you see now on February 18, there were clouds. The RVI is radar. Radar penetrates clouds, so we can see through clouds, and we get an imagery of the field even under cloudy conditions, right? And now this is a specific, it is adjusted RVI. It's an index that we have developed. As I mentioned, it will show you more variability in the field, based also on soil moisture and crop height, right? What did we see here today? Today we saw how we can easily design fertigation programs for proportional fertigation, for hydroponics, for open field crops. And we also saw at the same time, we can plan very precise irrigation schedules that use AI. I didn't talk much about what's behind the technology. Maybe we'll keep it for another session, okay? but I can just give you a glimpse of what I'm talking about. Let's see on the other field, because I saw a more interesting situation there. And one more thing I would like to mention, that it combines all this information, all right? What I'm showing you now with the radar and with the moisture and all that, you get notifications about that. You don't have to analyze the imagery. You don't have to analyze what's happening. The system tells you, all right? What do we see here? What we see here, you see the blue line and the blue graph and the green graph. And the blue graph is it's the growing degree days accumulation. Basically, this is a parameter that helps us determine the actual growth stage of the crop based on the crop model and how it develops. Now, and it takes into consideration the average temperatures and a base temperature or maximum threshold temperature of the crop. So it's crop specific. All right. Now, what we see here is that for the same planting date, if we look at today, even this year is much warmer for this specific crop than the average of the last 10 years. Okay. Now, this is a very important information because this will determine our harvest time. For instance, it will determine the occurrence of pests and diseases. It will determine water requirements. So we cannot just use generic protocols and say, hey, on February 27, I need to, or in February, this is the amount of water that I need to apply, and this is the amount of fertilizer, etc. No. Okay. Or this is the harvest date. It will change, and it changes according to the actual conditions in the field. So that's actually very interesting. And this is a place where we even show how we do that even compared to the past. So here, when we draw a field on the map, we get all the history of the field. All right, there's a lot of information that we obtain automatically. All right, planting dates. All right, previous planting dates, the variability of the field, of the soil in the field, previous water requirements, like we saw now, the GDD growing degree days, right? 10 years average. So there is a lot of information that gets into the system automatically, and we get visibility to basically every field in the world. That means every field that I draw now on the map, I can instantly get a huge amount of information about the field. All right. So yeah, again, thank you very much for participating today. I will stay here for another 5 minutes if you have any additional questions. So I'll try to answer them. If you have, let me share with you my contact details. So if you want to contact me, then feel free to do so. There we go. Yeah. So yeah, now I will see if there are any questions that might interest everybody. I will answer. If not, I will answer privately. But feel free. I will stay here, and I will put myself on mute if there is anything again interesting for the group and or large group today here. I will reply to everyone. If not, I will do that privately. And of course, interested to know if you can tell me on the Q&A, what in the chat, what you do, and what crops you use, and whether this presentation was helpful to you, and all that. I will be happy to hear, and of course, expect more webinars to come on these kind of topics. And my email is here, right? I hope you see it. Yeah, because I'm getting questions here. Yeah, so you see it. All right. Thank you very much. I will pause the recording here, and I will put myself on mute and stop the camera, but I'm still here. All right. So You can